Hey everybody, welcome back to College Algebra. Today we're in section 4.5 and we're going to be solving exponential and log equations. You may remember that in section 4.2 we looked at some simple exponential equations, and in section 4.3 we looked at some simple log equations, but today we're going a little more in depth with both types of equations, and we're going to look at something called the natural base and the natural log that's going to help us solve these equations. So let's get started. Okay, first let's take a look at the natural base. So there is a number that is frequently used as a base for exponential functions because it has some convenient characteristics that make it useful in calculus. And that number is called e, or Euler's number, but it's represented with a lowercase e. This number is irrational, like pi, and it is approximately equal to 2.71828. Now don't worry, because you do not need to memorize this number. Anything that we need to do with the number e we will do on the calculator, and your calculator has the number e already built in. Now what's so special about this number is that it occurs so often in natural growth formulas, and it is so convenient to use in calculus, which is all concerned about rates of change and how fast things are growing and changing, that this number is called the natural base. It is the natural choice anytime you want to find a formula to represent how something is growing. Now because e is the natural base, when we switch to log form, the log base e is called the natural log, and that makes sense, right? So instead of writing log base e like this, we write it like this. So ln stands for natural log. I know you feel like it ought to be NL because in English we say natural log, but in Latin the natural would come after the log part. So that's why the n comes last. So ln represents natural log. So we would read this ln x, or you could say natural log of x. But it means the same thing as this, but we just never write it this way. Okay, so we can switch between exponential form and log form with base e the same way we did with any other base, like we did in section 4.3. So let's just practice here and see what this looks like. So suppose we have an equation that's e to the x equals 15. Now I'm not interested in solving this equation right now, but I just want to practice changing from this exponential form into log form. So do you remember how we did this back in section 4.3? So if we had a base here and an exponent here, then we would write log with this base. So we would write log base e of 15 equals the exponent. Remember that? Okay, now from the last slide we know that we never leave log base e written in this form. So log base e is always written as natural log, or we represent that with ln. So I would write ln 15 equals x. And now this is something that you can evaluate on your calculator. By the way, your calculator only knows two bases, so if you wanted to evaluate, say, log base 2 of 7 or log base 5 of 18, you cannot evaluate those logs on a standard scientific calculator, but you can evaluate log base 10. When you look at your calculator, the log button, with no base written represents log base 10, and you also have a button for ln, which is log base e. So you could evaluate this using a standard scientific calculator. Alright, and now let's look at a natural log equation, and let's switch it back to exponential form. So I want to change it back into a form where it's written as a base e with an exponent equal to some expression. Okay, so the first thing I'm going to do is trade my natural log here for log base e. So I will write log base e of 3 plus x equals 8. So all I've done is change from natural log to log base e. They mean the same thing, but this one is standard and this one is just for our convenience. So I'm going to now switch into exponential form. So this would be the base and this would be the exponent. So I'll have e to the 8th power equals this argument, so equals 3 plus x. And then I could solve that if I wanted to. You can evaluate this on a calculator and get a decimal value, but what we will do in this section is we will just leave any solutions that contain the number e, we'll just leave them in exact form. So you wouldn't even need to evaluate this on your calculator, although you could if you needed to. Okay, so let's look at how to solve some exponential equations, and I just want us to remember what we learned how to do in section 4.2 so you can tell how the two types are different. So in section 4.2, we learned how to solve exponential equations by writing both sides in the same base. So for example, if we had 2 to the x plus 1 equals 16, we said before that if we could write 16 as a power of 2, then both sides would have a base of 2. So we would have 2 to the x plus 1 equals 2 to the 4th, because 16 is 2 to the 4th. And then we said that if we have 2 to this power equal to 2 to some other power, well then those two powers must be equal. If the bases are equal, then the exponents must be equal. So we then would write x plus 1 equals 4, and then we would just solve and we would have x equals 3. So that's what we did in section 4.2. But now, what will we do if we can't write both sides as the same base? So for example, what if we had an equation like 7 to the x equals 12? How can we solve that? Because 12 is not a power of 7, so I can't use the same method that I used up here. So this is the kind of equation we want to learn how to solve today. So in order to do that, we're going to use what's called the property of logarithms, and this is what it says. If you have a positive x and a positive a, as long as a is not equal to 1, then the following is true. If x equals y, so you have some positive number equal to some other expression, okay, then that can be restated as log base a of x equals log base a of y. In other words, if two things are equal, you can take the log of both sides with the same positive base, and then that statement will also be true. And you might be saying, well, how is that going to help? So that's what we're about to find out right now. So if both sides cannot be written in the same base, this is our strategy. First, we will take the natural log of both sides. In other words, we will write ln in front of the left side and ln in front of the right side. And then we will use our log properties to isolate the variables. So you remember in section 4.3 at the very end, we looked at the log properties. And so we'll use those log properties to help us isolate the variable. And then we'll use the calculator to evaluate any natural logs that we have to do. And by the way, you might be asking yourself, why does it have to be the natural log? Why do we have to take the natural log of both sides? Because the property says that as long as a is positive, we can do log base a on both sides and the property will work. So why not do log base 2 of both sides? Why not do log base 7 of both sides? Well, remember the last step says use the calculator, and our calculators don't have log base 2 or log base 7. Our calculators have log base 10 and natural log, which is log base e. So we do natural log of both sides simply because our calculators can handle it. We could just as easily do log base 10 of both sides and we would get the same answers. But you know what? ln is just a little easier to write than log base 10. So we do natural log of both sides just kind of as a convenience thing. Okay, and that's all it is, so don't let it worry you. So remember that example we looked at just a few minutes ago and we realized that our strategy we had in section 4.2 wouldn't work? Let's use our new strategy and see how it does on this example. It says solve 7 to the x equals 12. So our strategy is take the natural log of both sides. So I'll write natural log of 7 to the x equals natural log of 12. And see, it's still an equation because if 7 to the x equals 12, then natural log of 7 to the x equals natural log of 12. All right, so now I want to use my log properties to move this exponent down to the coefficient position. Remember our power rule for logs? So that exponent moves right down to the front like this. And now, natural log of 7 is just a number. So we can divide both sides by natural log of 7. That cancels it from the left side, and we're left with this, which our calculator can evaluate. So in your calculator, you will find the LN button, which is right below the log button. It's the third button down in the left-hand column if you're using a TI-30X2S. So you'll go natural log of 12, and then you'll need to close the parentheses. I hope you're doing this with me. So natural log of 12, close the parentheses, and then divided by natural log of 7. And this time you don't have to close the parentheses because we're going to press equal, and the calculator will automatically close your parentheses. And that's going to be approximately equal to 1.277. Now notice that the instructions here told us round the answer to the nearest thousandth. When you evaluate something like this, it's always going to have an infinite string of decimal places, and you will have to look at the instructions to know how many to keep. So nearest thousandth means we round to the third decimal place. So actually in the calculator, what it said was that x equals 1.276989408. But if we want to round to the third decimal place, then we have to look at the digit in the fourth decimal place, and if it's 5 or more, then this digit rounds up. Of course, y'all know that. So this would become 1.277. And here in example 2, this one looks a little bit different because the base is a fraction, but we don't treat it any different. We're still going to solve it the same way. So if you can't write 5 as a power of 1/2, which you can't, then what you'll need to do is take the natural log of both sides. So we will write natural log of 1/2 to the x equals natural log of 5. Then we use our log property to bring this exponent down to the coefficient position. So it's going to say x times natural log of 1/2 equals natural log of 5. And then we want to isolate the x, so we divide the left and the right by natural log of 1/2. So now we're ready to put this in the calculator. You're going to say natural log of 5, then close the parentheses, divided by natural log of 1/2, press equal, and you will have approximately negative 2.322. All right, now let's move to log equations. So the first thing we're going to do is look at some pretty simple equations that are very similar to the ones we saw in section 4.3, only now we will deal with the natural log, where before I think we always stayed away from the natural log. So just to remind you, if you have a single log expression on one side of an equation and a constant on the other side, like we did in section 4.3, then the way to solve it is to restate the equation in exponential form. So here we have an example. 7 times natural log of x equals 28. Now the first thing we need to do here is isolate this natural log so that we can switch into exponential form. So we need to eliminate this 7. You have a choice. You could use your log property to move the 7 back to the exponent position, so you would have natural log of x to the 7th, but your next step then is going to involve x to the 7th, and nobody wants that. So let's eliminate this 7 by dividing it out. So I'll start with my equation, and then I will divide both sides by 7. And that leaves us with natural log of x equals 28 over 7, which is 4. So now I have natural log of x equals 4. And now I can think of this as log base e and state it now in exponential form. So if I have log base e of x equals 4, then this is the base, so e is the base, 4 is the exponent, and x is the other side. So now the equation is solved, and this is the answer in exact form. Again, if you wanted a decimal value for this, you could use your calculator. You have an E button on your calculator. It's actually the second function of the natural log. So you could evaluate e to the 4th power, and it would be 54.598, blah, blah, blah. But For this example, it's not necessary because notice that this says state solution in exact values. This is exact. Once you put it in the calculator and get a decimal value, it won't be exact anymore. So this is exactly what we want. All right, let's try it again on this example. So natural log of 4 times x equals 1.5. So the first thing to do, since we don't have a coefficient here that needs to be eliminated, the first thing to do is think of this as log base e. Okay, now switching into exponential form, this will be our base, e will be the base, and then 1.5 will be the exponent, and then that's going to be equal to 4x. Of course, we're trying to solve for x, so now we want to isolate the x, and to do that, we'll divide both sides by 4, and that gives us x equals e to the 1.5 divided by 4. And this is the exact form of the answer. Again, you could evaluate this on a calculator and get a decimal, but it's not necessary here because it says state the solution in exact values, and that's what we have right here. Okay, what about log equations that have more than one log term? Well, whenever we have more than one log term, we will use our log properties that we learned in section 4.3 to condense them into one term, because you can't do anything else to the equation until you have one log term on the left and either a constant or one log term on the right. Now, if you do have a log term on the right, so if you have something like log base a of x equals log base a of y, then what you can do is just eliminate the logs and use the log property backwards from the way we did in the exponential equations. So if you have log base a of x equals log base a of y, then you know that x equals y. So after the logs are eliminated, you'll just solve for the variable. Now you have to remember when you do this that the log function is defined only for positive numbers. In other words, we can't take the log of a negative number. So any solution that causes us to have to take the log of 0 or the log of a negative must be discarded. So let's look at this equation. It says log of x plus log of 2x plus 1 equals 1. And notice that it says give the solution to the nearest thousandth. So if there is any rounding to do, we will round to the third decimal place. All right, now the problem with this equation, what makes it different than log equations we've seen before, is that we have log plus log. We have two log terms, and we can't switch into exponential form if we have two log terms. So we will use our log properties to put these back together. Do you remember back at the end of section 4.3, we learned that if you have log of one thing plus log of another thing, and those two have the same base, then you can write that as log of this times that. So that's what we're going to do. But by the way, what is the base of this log? Well, because the base is not written, remember, we know that the base is 10. So we're going to write log of this times this, okay, so x times 2x plus 1 equals 1. So I used my log properties to condense this into one log term. So one more time, if you have log plus log, then you make one log term out of that, but the two arguments are multiplied together. Okay, now remembering that this is base 10, we can switch into exponential form. So 10 is the base, and 1 is the exponent, and then that's equal to this expression. So that's going to be equal to x times 2x plus 1. Now, 10 to the first power is just 10, and we can distribute that x. So that would be 2x squared plus x. And notice now that we have a quadratic equation, basically, because we have an x squared term. So how do you solve a quadratic equation? So of course you want to get all the terms on one side and see if you can factor. So we'll subtract 10 from both sides, and that will give us 0 on the left equals 2x squared plus x minus 10 on the right. So we're going to try to factor this expression. Remember, factoring is reversing the FOIL process. So I need to figure out what times what makes 2x squared. So of course it's 2x times 1x. This minus sign tells me that the signs in my factoring need to be different. I don't know yet if it's minus and plus or if it should be plus and minus, but as long as I put down two different signs, we're in good shape. And now 10 is either 1 times 10 or 2 times 5. I'm going to guess that it's 2 times 5. Of course, I can't put the 2 here because that would create a GCF. So I'm going to try the 5 here and the 2 here. And let's see what happens. So how will I know that this factoring is correct? Only if outer plus inner adds up to positive 1x. So let's see. 2 times 2x is 4x, and then negative 5 times x is negative 5x. So 4x minus 5x adds up to negative 1x, but I wanted positive 1x. So the fact that I got the 1 that I wanted, but I didn't get the sign I wanted, tells me that I need to switch these signs. So if I try it with the plus here and the minus here, then I have negative 4x plus 5x. That adds up to positive 1x. That's what we want. Okay, so that's great. Now, if this times this equals 0, one of these factors must be 0. So first I'll find out what makes 2x plus 5 equal 0. So if 2x plus 5 equals 0, then 2x equals negative 5, and x equals negative 5 over 2. And then I have to find out what makes x minus 2 equal 0. So if x minus 2 equals 0, then x equals 2. So both of these are potential solutions. What I have to do now is test them in the original equation, because remember, I can't allow a solution that causes us to have to do the log of a negative number. So imagine right here, what if I substitute negative 5 over 2 right here? Well, then I would be doing log of negative 5 over 2, and I can't do the log of a negative number, so this solution is out. Let's try it with 2. So if I put log of 2, that's okay. And then if I do log of 2 times 2 plus 1, well, 2 times 2 is 4, and 4 plus 1 is 5, and that's a positive number, so that's okay. So x equals 2 is a legitimate solution. And so when I enter my solution in my lab, or if I'm working a test and I have to choose a correct answer, then the correct answer would be x equals 2. And I would need to ignore the solution negative 5 over 2 because it was an invalid solution. Let's try another example. So this one has natural logs on both sides. Now remember, we can't do anything to an equation if we have two log terms on the same side. So we'll need to use our log properties to combine these. Again, just like we saw before, these two log terms are added, and that means that we will write this as natural log of this times this. So on the left, I'll have natural log of x plus 25, and on the right, I'll have natural log of 4 times x plus 10. That's using our log properties to condense these two terms into one. Now, if natural log of this equals natural log of that, then I can say that this expression here must be equal to this expression on the right. So I can say now x plus 25 equals 4 times x plus 10. This equation doesn't look so bad to solve, so we're just going to distribute the 4. That will give us x plus 25 equals 4x plus 40. Of course, here you would subtract x from both sides, and that would give you 25 equals 3x plus 40. And now you would subtract 40 from both sides because you want to isolate the x term. And that would give you negative 15 equals 3x. Of course, divide both sides by 3, and you have x equals negative 5. Now we always, because this was a log equation, we need to check that this solution does not cause us to try to take the log of a negative number. So just plug it in here. You don't have to actually evaluate the log. You just need to make sure that this value would not come up negative or 0. So negative 5 plus 25 would be 20. So that's a positive number, so that's okay. And negative 5 plus 10 would be positive 5, and that's okay. Of course, this does not have a variable, so we don't have to worry about that. And that means that this is a valid solution, And so the solution is x equals negative 5. For our next example, we have a log base 2. So this one is actually very straightforward. It's almost exactly like what we did in section 4.3. We have a log with a base here, and we have a constant on the right side. So all we have to do is switch into exponential form. So this will be the base, and this will be the exponent. So we'll have 2 to the third equals all this stuff on the other side. Now, this is a binomial times another binomial, so in order to solve this equation, we'll need to evaluate 2 to the third, which is 8, and then we'll need to FOIL this out, or multiply these two binomials together. So first times first would be 3x times x, that's 3x squared. Outer times outer is negative 12x, inner times inner is negative 7x. Negative 12x minus 7x is negative 19x. And then last times last would be positive 28. So this is a quadratic equation. In order to solve it, we hope that we can use factoring, but we don't know until we eliminate this 8 from the left side. So we'll subtract 8 from both sides. That will leave us with 0 equals 3x squared minus 19x plus 20. We need to try to factor this. So I'm breaking my trinomial into two binomials, and I know that first times first is 3x squared, so that's got to be 3x times 1x. Now, this sign tells me that the signs in the parentheses are the same, and if they're the same, they must both be whatever this is. So this tells me that they're both negative. All right, now, choices to go here, two numbers that multiply together and give us 20, would either be 1 times 20, 2 times 10, or 4 times 5. I'm going to try 4 times 5, and so I'm going to put 5 there and 4 here. And let's check and see if outer plus inner adds up to negative 19x. So outer times outer is minus 15x, inner times inner is minus 4x. Negative 15x minus 4x does give us negative 19x. That's what we wanted. So this factoring is correct. Now we can solve. If this times this equals 0, then one of these factors must be 0. So we need to find the x value for each one that causes it to equal 0. If 3x minus 4 equals 0, then 3x equals 4, and x equals 4/3. If x minus 5 equals 0, then x equals 5. Okay, now we need to check and make sure that neither one of these causes the argument here to become negative, the whole argument. So what I'm going to do is plug in 4/3 and see what happens to this whole thing. 3 times 4/3 would be 4. Now 4 minus 7 is a negative number, but 4/3 minus 4 is also a negative number, and a negative times a negative is a positive, so this solution is okay. If I plug in 5, 3 times 5 is 15. 15 minus 7 is a positive number. 5 minus 4 is a positive number. Positive times positive is a positive number, so this solution is also okay. So sometimes it happens that both solutions work out, and so in this case, the solution set is 4/3 and 5. Now let's look at example 6. So this one says log, by the way, base 10, right? Log of x minus 10 minus log of x minus 6 equals log of 2. Now, in order to condense these two terms into one, this is a minus, so I would have to use the quotient rule for logs, and it would look like this. Log of x minus 10 over x minus 6 equals log of 2. And we could go ahead now and eliminate the log from both sides. But notice that because of this minus sign, I've got this denominator, and I mean, if you're comfortable with that, you can go ahead with it, but I'm going to bet that most of you would like to not have to see this fraction. So let me show you a trick. Instead of having this negative log term on the left, why don't we move the whole log term over to the right where it will be positive? So that will give us log of x minus 10 equals log of x minus 6, so we just move this over to the right and it becomes positive, plus log of 2. Now we can use our product rule for logs right here. And so we will condense these two terms into one. So that's going to give me log of x minus 10 equals log of this times this. So I'm going to write log of 2 times x minus 6. Now I can eliminate logs, because if log base 10 of this equals log base 10 of this, then these two expressions must be equal. So x minus 10 equals 2 times x minus 6. Distribute your 2, so that would give you 2 times x minus 2 times 6, which is 12. Subtract x from both sides. That will give you negative 10 equals x minus 12. Now add 12 to both sides. That will give you 2 equals x. So that is our potential solution, but we need to check it. We need to make sure that it doesn't cause any negative arguments over here. So let's pretend that we put a 2 in this place. So 2 minus 10, that's negative 8. We can't do the log of negative 8. So that right there is enough, but we also, 2 minus 6 would also be negative. So problems both places, it only takes one problem to cause us to have to scrap that whole solution. And since that was our only potential solution and we had to get rid of it, that means that this equation has no solution. So that can happen. All right, here is another example. So this is log base 8 of x plus 2 plus log base 8 of x plus 4 equals log base 8 of 8. Now, remember, a log is an exponent, so if you wanted to evaluate log base 8 of 8, you could. You could say the exponent of 8 that gives me an 8 is 1. You could do that, and then you could combine terms. I would not do that because it's going to be so easy just to eliminate logs. I would leave the log on both sides. But I would have to combine these two log terms into one. So we're going to write log base 8 of this times this. So log base 8 of x plus 2 times x plus 4 equals log base 8 of 8. Okay, now, if log base 8 of one thing equals log base 8 of something else, then those two things must be equal to each other. So now I can say x plus 2 times x plus 4 equals 8. Go ahead and FOIL this out, so that would be x squared plus 6x plus 8. Where'd the 6x come from? Outer plus inner would be 4x plus 2x, that's 6x. And that equals 8. Now, in order to solve this quadratic equation, you know we need a 0 over here. So we're going to subtract 8 from both sides. That's going to give us x squared plus 6x equals 0. This is no longer a trinomial. So the way to solve this is not to try to make two binomials, but to factor out a GCF of x. So if we factor out x as a GCF, that gives us x times x plus 6 equals 0. And now, if this times this equals 0, either x equals 0 or x plus 6 equals 0, which means x equals negative 6. I need to test each of these in the original equation. You can't test it here. You need to go back to the original equation and test. So if I put 0 in here, 0 plus 2 is positive 2, so that's fine. 0 plus 4 is positive 4, so that's fine. So 0 is a valid solution. But if I plug negative 6 in, well, negative 6 plus 2 is a negative 4. So this is an invalid solution. And so I would write my solution set as just x equals 0. And finally, our last example together, this is going to be natural log of 5 plus 4x minus natural log of 3 plus x equals natural log of 3. So we've seen this before where we had this negative log term. You can use your quotient rule for logs and write this as the natural log of a fraction where you would have 3 plus x on the bottom. But instead of that, let's do what we did last time. Let's take this negative log term and move it over to the right where it will be positive. So that would give us natural log of 5 plus 4x equals natural log of 3 plus x, which is positive now that we moved it to the right side of the equation, plus natural log of 3. Now we can use our product rule for logs over here and combine these two into one term. So we'll have natural log of 5 plus 4x equals natural log of 3 times 3 plus x. Now, if natural log of this equals natural log of that, then this and that must be the same. So now we say 5 plus 4x equals 3 times 3 plus x. Distribute your 3. So 3 times 3 is 9, 3 times x is 3x, and we'll just solve this little linear equation. So the first thing I would do is subtract 3x from both sides. That will give us 5 plus x equals 9. And now subtract 5 from both sides, and we have x equals 4. And we need to test that 4 in both of our log terms that have variables. So 4 times 4 is 16. 16 plus 5 is a positive number. 3 plus 4 is a positive number, so this is good. And our solution set is just x equals 4. All right, these take a little bit of practice to get used to because they come in so many different forms. But if you'll practice, you'll be fine. And, you know, as always, reach out to your instructor if you get a little stuck. And keep pushing on. You're almost to the end of the course, so good luck.